Turn our attention to example number 5. This is one I'm going to ask you to try here in just a moment, but I'll at least get us started. Let's determine whether the following series is convergent or divergent, and of course if it converges, let's find its exact sum. Now, when I look at this problem, I at first can be pretty intimidated. I mean, there's a lot of mess that's kind of going on here. But what we'll see is that so far, we've only really identified one approach to determining if a series converges or diverges. We know that in general, our approaches are find S sub n, and we can do that in one of two ways. We can either do that by finding this as a telescoping series, right? That is, start writing out the partial sums and seeing some things cancel. Or we might be able to see that this could be a geometric series, and if it is, in geometric series, I actually don't even have to find the S sub n because I already have that cool theorem that we talked about in the past couple videos. So, well, let's think about then what the general shapes of these different series actually look like. Remember that a telescoping series usually had like something minus something else, so that way when I wrote out my S sub n, I would have some things that cancel. And I know that my geometric series has a shape of a times r to I minus 1. Or in this case, I guess I could replace that value of I with the variable that we have here, which is n. Well, if I look at which of these things I might be closer to at the moment, am I closer to being something like a value minus something, or number times number to a power n minus 1? I might be a lot closer to geometric. And if this looks like it might be geometric, maybe with enough algebra, I can go ahead and re-express this as an a times r to the n minus 1. Let's make that our general strategy here. And so I'll go ahead and I'll write out the following. I'll state that we rewrite the series knowing that, and I'm going to go ahead and think about how I can take this initial expression that I was given and rewrite that as, again, in a times r to an n minus 1. Go ahead, pause the video right here, and see if you can actually go through and do that. Can you do some algebra to try to get this into this geometric form? All right, well, hopefully you took some time to try to work on that. Let's see what I would have done. Notice that the first thing I could do is rewrite this as 8 to the 2n times 8 to the negative 1 times 3 to the third times 3 to the negative 4n. That, of course, is equal to 64 to the n times a 1 over 8 times a 27 times a 1 over 3 to the 4n. Now I can rewrite that a couple more times. I'll write that as 27/8 times 64 to the power of n times, let's see, 3 to the 4th power is 81, so that's 1 over 81 to the n. Notice then I can actually rewrite this one final time as 27 over 8 times 64 over 81 to the power of n. We've almost done it here. We've almost gotten it to look like a times r to the n. Oh wait, we want n minus 1. Well, that's actually really simple to do. Remember that you can simply just go ahead and take a 64 over 81 kind of off of the stack of them that you have here, which of course would leave you with one less on the stack. Now, simplifying some stuff over here becomes easy as well. Notice that 64 over 8 is going to give us 8, and 27 over 81 is going to leave us with 3, in the denominator, that is. So we're going to have like an 8/3 and then a 64 over 81 to the n minus 1. And we got it. So that means that our starting series, which was 8 to the 2n minus 1 times 3 to the 3, oops, that should be a minus 4n, that series is actually identical to the given series, 64 over 81 n minus 1. Notice that I kind of knew that, again, this was a possibility for us to maybe get to here, because when I looked at the series, I noticed that n, that variable that I'm counting with, was up in the exponent, just like it is in a geometric series. And that's a great tip-off that I might be working with something that's geometric, or that I can get into this geometric form. And so I can say that this here is a geometric series with a equaling 8/3 and r equaling 64/81. And now I know that since the absolute value of my r is less than 1 here, we know that the series converges, and moreover, we can actually state precisely what it converges to, because that general formula of that a over 1 minus r can still be used. So a over 1 minus my r. Notice that's going to give me 8/3. Let's see, it's going to give me, my denominator there was that 17/81. If I rewrite that, that's 8/3 times 81/17. And this is going to be a little bit ugly. Let's see, I can simplify that. That creates a 27. I don't know, 8 times 27. What is that going to be? 160 and 56. So what is that? 216 out of 17. I got it. The series converges, and it specifically converges to 216/17.